We have an example problem here. A block of unknown mass is attached to a spring with a spring constant of 6.5 newtons per meter and undergoes simple harmonic motion, meaning ideal motion, with an amplitude of 10 centimeters. When the mass is halfway between its equilibrium position and the endpoint, its speed is measured to be 30 centimeters per second. Calculate the period of the motion. All right, so spring constant, lowercase k, 6.5 newtons per meter, amplitude A, 10 centimeters. When the mass is halfway, so if this is equilibrium, and this is the maximum displacement of 10 centimeters, it's telling us that the mass is halfway between there. So we could say x is half of the amplitude. The speed, v, is 30 centimeters per second. Now, I don't actually know that the mass is on the right side and moving to the left. It could be moving to the right, or it even could be over here at a position of negative 1/2 a. In the situation of this simple harmonic motion, this ideal motion, it doesn't matter which side it is on. Now, there's two ways to go about this. We could write the equation or write an equation that could describe the motion, the position of this mass at any moment in time, and take the derivative to write the velocity, and then relate those with the values that we've been given. Or we can look at conservation of energy. Either way is fine. My instinct is to use energy because conservation of energy is often a simpler way to write out our equations. So I'm going to go ahead and do that. Energy. I know when the mass is out at the amplitude, all of the energy would be potential. I know A, I know K, so I could find this total amount of energy. At the moment in time that they've given us this speed and where the mass is, the spring is still stretched, so there is some potential energy, but the mass is also moving, so there is also some kinetic energy. Well, I know K, I know the amplitude that was given to me. I know x at this moment in time. I know v at this moment in time. And that will allow me to solve for m. Now, why do I want m? Well, period is always related to omega. Omega is 2 pi f, which is also going to be 2 pi over t. So our period is going to be 2 pi over omega. But for a mass spring system, this simple harmonic motion, omega is the square root of k over m. So the period ends up being 2 pi times the square root of m over k. So we need the mass to determine this period. We already have the spring constant. And so this is why we need to find a way to find the mass. And that's how this energy will come in handy. All right, so I can see that there is a 1/2 in every term. So I'll go ahead and cancel that out. I need to bring the kx squared to this side. I know v, I'm solving for mass. I'm going to go ahead and factor out the k just for simplicity and plugging it into my calculator. And then I end up needing to divide by v squared. So K 6.5 newtons per meter. A 10 centimeters. I'm going to go ahead and put that in meters. I'm in the habit of putting things into SI units. X is half of A, so that's going to be 5 centimeters. So 0.05 squared. The speed, I will want that in meters per second. So 0.3, and that needs to be squared. So the mass ends up being 0.54. Since we have 3 sig figs given in the problem, I'm going to take this value out at least one more than that, since I'm not at a final answer, and then round to the 3 sig figs at the very end. Now technically, because the meters squared up here is canceling with the meters per second, the meters in there, we could technically have left that in centimeters and it would have worked out and still given us kilograms. But the safe bet is to put our units in SI units so that we know we're coming up with an SI answer. So now to plug our values into the period. K 6.5. If you recall, a Newton per meter is also a kilogram per second squared. I'm going to write it that way so I can see my kilograms cancel. So plugging this in. Now is when I want to round to the 3 sig figs. And keep in mind, you cannot round to less than 3 sig figs and then give an answer in 3 sig figs. You always have to keep more in the intermediate steps. I actually used the value that was in my calculator, so I used more than the 4 that I wrote down since it was already in my calculator. But this particular system will oscillate with a period of 1.81 seconds. So that means it takes 1.81 seconds for this particular mass spring system, the mass, to move through a full oscillation.